Hello, fellow chemists. Jolley here. Today we are going to be talking about how to draw a Lewis structure, and I call it the Jolley way because my approach is a little bit different than probably what you'll find in most textbooks or other places online. If it works for you, great. If not, there are a lot of systems to be able to draw a Lewis structure. All right, so the first question is, what is a Lewis structure? A Lewis structure is a pictorial representation of a molecule and its electrons. But the key is it is in 2 dimensions. These molecules are in 3 dimensions and we're trying to draw them in 2 dimensions. So eventually we'll have to visualize them with some depth. But we're going to start with just 2 dimensions. All right, we're going to try and put the molecules together in the most logical bonding locations with all of their electrons, and we're going to make the best one. Now this can get really frustrating at first because you can draw a lot of different kinds of Lewis structures. I don't want every kind of Lewis structure. I want the one that is the best. And the first question is always, well, how am I going to know if it's the best? So I have come up with a set of rules for you, and here's the general idea. If the elements all have their octets full if possible, that is a great thing. If they have the fewest formal charges, that's another great thing. And then that chemical common sense idea, did you put the negative on the most electronegative? Did you put a positive on the most electropositive? Just kind of common sense things like that. But hopefully if you work through this system, you will come up with the best one. And the more you do, your chemical instincts will get to the point where you can recognize if it is a good Lewis structure that has been drawn. All right, some points to remember before we get started. And then you're looking at this handout that I have for my students, and this is available online for my students or in my notes and in the lab manual. It's part of the Jolley way of figuring out how to do chemistry. All right, so what do we need to remember? A bond consists of 2 electrons. If it's not in a bond, the electrons like to be paired up. Electrons do not like to be by themselves. That's called a radical, but in this case, I call them lone electrons or loners and bonding sites. All right, a single bond can be drawn with 1 line, and that represents 2 electrons. A double bond is drawn with 2 lines, and that represents 4 electrons. A triple bond is drawn with 3 lines, and that represents 6 electrons. Terrible drawings, but we get the point. All right, so first of all, bonds can be written with lines. You don't necessarily have to have the lone pairs or the electrons in there. That is completely up to you, but it does make the picture a little bit cleaner. All right, a bonding site is an unpaired electron. Now remember, electrons do not like to be unpaired. So I'm going to give you an example of there is an example of something that oxygen can do. What are the individual pieces? This I would call a loner or a bonding site. This one and this one are lone pairs. And this would be a bond, specifically a covalent bond, and because there's only 1 line, it would be a single, and so it is representing 2 electrons. And then if you split that bond in half, this one belongs to oxygen, and this one belongs to the other atom. All right, so a bonding site, again, is this loner electron. Now we have to talk about how many things can go around each atom, and that is called an octet. All right, so octets, now keep in mind it comes from the word 8, but not every atom has to have 8. It includes all the electrons that are owned and all the electrons that are shared. So right here, this one was owned, this one was shared. So if I was to count the octet, I would count up all of them around the individual atom. And then some points. Hydrogen and helium both have an octet of 2. Boron, because it is so small, it doesn't have very many protons in that nucleus, generally likes to only hold on to 6 electrons. Carbon, nitrogen, oxygen, fluorine, neon, silicon is 8 and only 8. And if you'll notice, I'm not using the metals because this is for covalent bonding. So I use only the non-metals and the metalloids. So carbon, nitrogen, oxygen, fluorine, neon, and silicon. This is the N equals 2 plus silicon. They are 8 and only 8. And then phosphorus, and anybody larger on the periodic table, has to have at least 8, but they can't expand because they have the D subshell. So anybody in the N equals 3 and on can expand. So why can't silicon? Silicon doesn't have enough protons in its nucleus to expand very well. All right, another unique thing, carbon is the only element that will bond to itself quite willingly when given a choice. Any other element, if there is another choice, they will not bond with themselves. Carbon is very unique that way, and that leads to a whole area of chemistry called organic chemistry. All right, always place hydrogen and fluorine and any ion electrons in the structure last. And remember, hydrogen loves to go to the most electronegative element. And just a generic, octets are generally more important than formal charges in the big scheme of things. All right, what I'm going to do first is I'm going to go through these steps, and then we're going to draw a whole bunch of them using this step. So I suggest you do go and print out my How to Draw a Lewis Structure the Jolley Way so that it can be right there with you, but I'm going to give you the pieces here. All right, so let's go to the next portion. Clear this out. Take me a minute to get the new section. All right, let's paste this in. All right, drag that up a little bit. All right, step number 1. We would place the least electronegative element or the most electropositive in the center. And again, do not choose hydrogen and fluorine unless there's no other option. All right, so place the least electronegative or the most electropositive in the center, and place the valence electrons of that atom around it and keep them unpaired for as long as possible. And remember, because this is in 2 dimensions, that's 4 locations around it. So we're going to do an example like this one. We're going to go CH4O. All right, so of these, what is the least electronegative, the one that's furthest away from fluorine? Okay, that would be carbon. So we're going to put carbon in the center, and then we're going to put its valence electrons around it. All right, so I have just done this step, and I have just done this step. I kept them unpaired for as long as possible. And so my next question is this. How many good bonding sites are there, or how many lone electrons are there? Well, right now, there is 1, 2, 3, 4. So carbon has 4 really good bonding sites. How many substituents, or how many other atoms, am I trying to put around it? Keep in mind, don't include hydrogen and fluorine yet. All right, so if I can't include those, I only have 1 substituent that I'm trying to put around it. So, are there enough bonding sites for the remaining atoms or substituents? Well, right now I only have 1, so the answer is yes. So I'm going to create a single bond by sharing the electrons, 1 from each atom, and I'm going to use that with a line. So I'm going to draw this line in blue. So it does not matter which direction I go. I could have gone any direction with this oxygen, but that is representing that there's 1 from carbon, there's 1 from oxygen, and so this is 1, 2, 3, 4, that spot's used, 5, and 6. So oxygen has 6 valence electrons. So I have now created a single bond between carbon and oxygen, and I've written the valence electrons of oxygen. All right, do I still have loners? And the answer is yes, I still have loners. In fact, I have 1, 2, 3, and 4. I have 1, 2, 3, and 4. How many things do I still have left to put on? If these match, I'm just going to put on the hydrogens. And the answer is yes, they actually do match. So one's going to go there, one's going to go there, one's going to go there, and one is going to go there. Now normally I would ask some more questions, but we're just going through the generic steps right now. So, are there enough bonding sites for the remaining? I said yes, I put the oxygen on. If I had said no, I would have taken a lone pair and I would have split it up. Alright, so let's go on to the next page. And then we'll do some complete ones. Takes me a minute to cut and paste here. Alright. Alright, so our next step would be to ask, are there any bonding sites left? And remember, we did that. If the answer is yes, are there enough hydrogens, fluorines, or ions to fill those? And we said yes. So we created a bond with the hydrogens and we finished it out. If the answer had been no, are there any lone electrons on adjacent atoms? All right. Now I know this is kind of going through kind of quickly, but I'll come back and I will do one of each kind. All right, so there's number 4. The next step would be we would check our octets, then we would check formal charges, we would check for resonance structures, and then we would do our final check, which is called the chemical common sense check. Now, we need to go through an example of each kind, and so if you have this open with you, don't try and follow it exactly. Use it more when you get stuck. But I follow this pretty much in order every time I do a Lewis structure. All right, so I'm going to clear this page, and we're going to start with that easy one, which is the CH4O. All right, so our first one is CH4O. Now, of course, we just did this one, but I want to work through the entire process. So step number 1. Who should go in the center? Who is the most positive or the least electronegative? And that will be carbon. Put carbon in the center. Put its valence electrons around it. How many good bonding sites are there, or how many loners are there? There's 4 bonding sites. How many things are you trying to put around it? Okay, so how many things, or how many substituents, atoms, whatever you want to call it, how many things are you trying to put around it? Technically, at first there's 1, but then there's 4. Okay, so the oxygen is most important, and then we have 4 hydrogens, but this is the one I start with. Do I have enough bonding sites for my 1 oxygen? The answer is yes. So go ahead and make a single bond to my oxygen, draw its lone pairs in. Do I still have bonding sites available? And the answer is yes. I have 1, 2, 3, 4. Do you still have 4, either a hydrogen, fluorine, or ion electrons that can take those spots? And the answer is yes. So go ahead and now bond those hydrogens up. Are there any loners left? No. Go check your octets. All right, now remember, an octet is everything that's owned and everything that is shared. So we're going to do hydrogen first, and you have to do it for every atom. So 1, 2, hydrogen's fine. 1, 2, hydrogen is fine. 1, 2, hydrogen is fine. 1, 2, hydrogen is fine. So hydrogen has 2 electrons in every case. Let's do carbon. 1, 2, 3, 4, 5, 6, 7, and 8. So carbon has 8, which it's supposed to have. Let's do oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Oxygen is also supposed to have 8. So those two are both fine. So my octets are complete. I'm then going to go to formal charges. Now remember, formal charges is only what it owns. So every time there is a bond, carbon only owns half of that. Oxygen only owns half of that. So when I'm doing formal charges, it's however many it brought to the party, which is its valence electrons, minus how many it owns. So for carbon, it brought 4 to the party, and now it owns 1, 2, 3, and 4 for an overall 0 or neutral. It has no formal charge. The oxygen brought 6 to the party, and it still owns 1, 2, 3, 4, 5, and 6. Now notice it owns the lone pairs, so it owns all 4 of those electrons from the lone pairs. So it is also neutral. And then each of the hydrogens, they brought 1 to the party, and they each own 1 still. So each of the hydrogens are neutral with no formal charge. All right, so we have our molecule. It has complete octets. It has no formal charges. The next question would be, does it have resonance? And the answer to this question is, did you put a multiple bond anywhere? And what did I just do? Did we put a multiple bond anywhere? And the answer is no. And the answer is no. So they are all singles. So there's no resonance. All right, let's check for chemical common sense. Are there any formal charges? No. Does anything look odd? Did you put electrons one location when you could have put them another? No. So everything is complete. So this is the best Lewis structure. Let me redraw it. Okay, now notice I drew that hydrogen. I drew this hydrogen a little bit different. It does not matter. It does not matter. That is the best Lewis structure for this specific formula. All right, let's try another one. All right, let's try SO2. All right, so who is the most electropositive or the least electronegative? That would be sulfur. Put it in the center. How many valence electrons does it have? It has 6. So 1, 2, 3, 4, 5, and 6. How many good bonding places does it have? It has 2 good bonding places. How many things are you trying to put around it? I'm trying to put 2 around it, so it looks perfect. So I'm going to make a single bond to that oxygen, and the oxygen also has 6 valence electrons, and I'm going to put another oxygen around it, and it also has 6 valence electrons. So I now have 2 single bonds to oxygen, and then the sulfur has my lone pairs. All right. Are there still good bonding places? And the answer is yes. I have a loner right here, and I have a loner right here. Are there any other atoms that I'm supposed to put on? No. There's no hydrogens. There's nothing there. So I'm going to have to complete this molecule using what I have. Now, are there lone electrons on adjacent atoms? Now keep in mind, there's a lone electron right here, and there's a lone electron right here. But remember, I'm the one that paired these up. So I paired those up. So are there lone electrons on adjacent atoms? I call that screaming. Those are screaming to be able to make a double bond. So I'm going to take this one right here, and I'm going to take this one right here, and I'm going to share them and make a double bond. So this one is not there anymore. That one's not there anymore. They are now right here. And notice that's going to leave this one and this one. They're going to pair up and they're going to make that double bond. So let me redraw this. So what I have now is this. All right, are there any loners left? And the answer is no. All right, go check your octets. Now, the moment I unpaired those, that usually implies that I am going to expand. And so the first question is, can sulfur expand? And if you look on the periodic table, it is in the N=3 shell, and it's past phosphorus, so the answer is yes. All right, so it can expand. So let's check those octets. So around sulfur, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 electrons around sulfur. Is that okay? Yes, because it can expand. All right, let's check those oxygens. 1, 2, 3, 4, 5, 6, 7, and 8. Is oxygen supposed to have 8? Yes. 1, 2, 3, 4, 5, 6, 7, and 8. Is oxygen supposed to have 8? Yes. So all of my octets are full. All of those octets are full. All right, now let me get rid of those colors. Okay, we have checked the octets and everybody is completely fine. We're now going to do formal charges. And remember, formal charges only deal with what you own. So remember, oxygen owns half those, sulfur owns half those. So sulfur, it brought 6 to the party, and it now owns 1, 2, 3, 4, 5, and 6. So that's perfectly fine. So it's overall neutral. Each oxygen, so we'll call this oxygen 1 and this oxygen 2. Oxygen 1 brought 6 to the party, and it owns, switch colors here, it owns 1, 2, 3, 4, 5, and 6. So it's overall neutral. And oxygen 2 brought 6 to the party, and it owns 1, 2, 3, 4, 5, and 6. And it is also neutral, so there are no overall formal charges. All right, I've checked my octets. I've checked my formal charges. Did I put a multiple bond in one location when I could have put it in an identical location? Now, I did put a multiple bond in here, but I didn't choose between locations, so there is no resonance. And I am left with my chemical common sense. The only thing that was unique here is I expanded sulfur. And I've already answered this question, but it's a nice double check. Can I expand sulfur? Yes, because it's in the N=3. So, everything works out perfect. This is the best Lewis structure for sulfur dioxide. All right, now I am going to draw it wrong. Okay, I'm going to draw it wrong for you now, and we're going to do a compare and contrast. All right, so let's say that I got done and this was my structure. All right, so let's just make sure. Sulfur brought 6 electrons. Oxygen 1 brought 6 electrons. And oxygen 2 brought 6 electrons. So I should have 18 electrons in there somewhere. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. All right, so I have all my electrons in there. Now, if I had come up with this structure, if you will notice, it looks a little bit odd compared to the other. So let's check octets first. Let's check octets. All right, let's do sulfur first. 1, 2, 3, 4, 5, 6, 7, 8. All right, sulfur looks absolutely fine. Let's check our oxygen. 1, 2, 3, 4, 5, 6, 7, and 8. That oxygen looks perfectly fine. How about this one? 1, 2, 3, 4, 5, 6, 7, and 8. All right, so my octets all look pretty good, so I'm not quite sure what's wrong yet. Let's check our formal charges. All right, so half of that bond, half of that bond. So sulfur, it owns right now 1, 2, 3, 4, and 5. But I know sulfur brought 6 to the party, and it only owns 5, so that's an overall +1 charge. So that's a +1 right there. Oxygen 1, it brought 6 to the party, and it owns, let me do a different color here. One, 2, 3, 4, 5, 6, 7. It owns 7 at the moment for an overall -1. And oxygen 2 brought 6 to the party, and it owns 1, 2, 3, 4, 5, and 6. So it's neutral. Now, if you'll notice, overall, a +1 and a -1 still is overall neutral, but this molecule carries formal charges where our other molecule did not. And the best Lewis structure has complete octets with the fewest formal charges, and that's why this one isn't quite as good as the other one. And then another question would come up for this one. Did I put a multiple bond in one location when I could have put it in an identical other location? And the answer is, did I put a double bond in one location when I could have put it in the other location? Because I could have drawn this like this just as easy. And if you'll notice, these are resonance structures of each other. They only differ in the location of a multiple bond. So, why is this not as good as the original? This one has no formal charges. And remember, nature loves neutral, or the lowest energy state. So this is the best Lewis structure. Are these Lewis structures? Absolutely. But they're not the best one. All right, let's play with that resonance idea. Let's do an example for resonance. All right, let's take the carbonate ion. All right, so who's the most positive? Who should go in the center? Well, it's going to be carbon. How many valence electrons does it have? It has 4. 1, 2, 3, 4. How many good bonding places do we have? We have 4. How many things are we trying to put around it? Not including hydrogen and fluorine. We have 3. Do we have enough bonding places for all of those atoms? And the answer is yes. So go ahead and put them on. So there's an oxygen with its 6 valence electrons, an oxygen with its 6, and an oxygen with its 6. Notice there is still one missing. Do you still have loners? The answer is yes. We have 1, 2, 3, 4. Now this is what I call really screaming. Are there loners on adjacent atoms? So the center atom plus one adjacent, the one right next to it, do they both have a loner? The answer is yes. And in fact, it has it in 3 different locations. But I only have one loner, so I'm only allowed to use it once. So I'm going to pair that up. That's screaming to make a multiple bond. So I'm going to get rid of that, and I'm going to make a multiple bond, and now these 2 are gone. All right, back to the question. Do you still have loners? And the answer is yes. I still have 2 loners. Is there anything that you have not included so far? And remember, this is where I would look for hydrogens, fluorines, and ion electrons. And notice this is a -2, which means there's 2 extra electrons that I get to put in. Surprise! guess where they go? One goes right here, and one goes right there, okay? All right, let me go back to my question. Are there any loners left? And the answer is no. Now I check my octets. So let me clean this up just a little bit. So that one's gone. And this one's gone. See if I can get it. Alright, it's not beautiful, but that's a little bit better. Okay, so there's no loners, and I'm going to check my octets. Alright, so 1, 2, 3, 4, 5, 6, 7, 8. So this oxygen has 8 electrons, and it's fine. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. It has 8 electrons, and it's fine. 1, 2, 3, 4, 5, 6, 7, and 8. This one has 8 electrons. And this carbon has 1, 2, 3, 4, 5, 6, 7, and 8. It has 8 electrons. So it has a wonderful octet for every atom. The next step would be, are there any formal charges? Now, I put extra electrons in there, so I should be expecting some formal charges. All right, so remember, everybody owns half of their bond. So for carbon, carbon brought 4 to the party, and it owns 1, 2, 3, and 4. So it's neutral. We'll call this oxygen 1, call it oxygen 2, and we'll call it oxygen 3. So oxygen 1 brought 6 to the party, and it owns 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. Look, it's neutral. Oxygen 2, however, has 1, 2, 3, 4, 5, 6, and 7. Okay, that shouldn't be a surprise because I'm the one that put it there. And then oxygen 3 brought 6 to the party, and it owns 1, 2, 3, 4, 5, 6, and 7. It overall has a -1 formal charge. So if you add those up, overall this whole molecule has a net -2 charge, which means it's ionic, but surprise, I knew that. I knew that. All right, so we have done our octets, we've done our formal charges, so I would put a formal charge right there, and I would put a formal charge right there. My next step is, should I draw resonance structures? Now I'm going to clean this up so we can have a nice, pretty new molecule. All right, let me redraw what we had here. So we had, let's go back to black. We had a carbon, we had an oxygen, and a double bonded oxygen. Then draw in their lone pairs. And this one had a formal charge, and this one had a formal charge. So there's the molecule that we just came up with. So I checked my octets, I checked my formal charges. The next step is, should I draw resonance structures? Did I put a multiple bond in one location when I could have put it in identical other locations? Now just a note, this is a very simplified definition of resonance, but it's a place to start. Eventually you'll just play with moving pi electrons, but that's for the future. But this is the place to start. Did you put a pi, or did you put a multiple bond in one location when you could have put it in another? And the answer was yes. So you need to draw it with every possibility. Alright, so I'll put it there. Keep the same backbone. Notice I have the same backbone, if you will. So this, whoops. I have kind of this T picture going. Keep that same backbone when you're drawing your resonance structures. Alright, so I have the same backbone. Let me put in my lone pairs. Alright, was there any other location I could have put it? The answer is yes. Notice I'm sticking with that same backbone idea. And there's my resonance. All right, so those are my three possibilities. How do you tell me that they're not all just new ones? You show me the double-sided arrow that indicates resonance structures. And the question is, are you telling me that there's three structures that exist? Okay, are there three structures? And the answer is a big old no. It is a hybrid, if you will, of all three. But the only way you can tell me that is either to draw all three of them or to draw the hybrid. Now the hybrid just takes a little getting used to, but you would draw it something like this. And you can see why we don't teach you to start drawing the hybrids. But this is what really exists. If I took a picture of it, would I see two single bonds and one double bond? No. We can actually take a picture of this, X-ray diffraction, and there is not two single bonds and one double bond. There are three identical, somewhere between a single and a double bond. So this is actually the best representation, but that's hard to just be able to do when you're first starting. So how are you going to tell me that you know none of these are actually correct? You're going to draw them all. You're going to draw them all. And that is the reason that you need to draw them, is you recognize that not one of those exists. It's actually some kind of hybrid of the three, or of however many that you have. All right, so there's another example. Let's try another expansion. Let's clear this out. Let's try SOCl2. It's called thionyl chloride. So step number 1. Who should go in the center? Now remember, oxygen and chlorine are two of the most electronegative, so it's going to be sulfur. How many valence electrons? It has 6. All right, now notice I'm starting to shortcut. I recognize that there were 6, and I know this pattern, so I have 2 good bonding places. How many things am I trying to put around it? Remember, don't count hydrogen and fluorine, but if you'll notice, I have 3 atoms or substituents I'm supposed to be putting, and I only have 2 good bonding sites. But that's okay. I'm the one that paired these up, so I'm going to unpair them. So I'm going to unpair them. Wait a second, are you allowed to do that? Remember, this is just a visual representation. It really doesn't, follow, ooh, can you move over here? Can you move over there? Those electrons do whatever is electronically or the most stable. So I'm going to unpair those electrons. Hey, how many good bonding places do I have now? I have 4, and I have 3 things to put around it. All right, go ahead and put them. So I'm going to put the oxygen right here. The oxygen has 6 valence electrons. The chlorine has 7. All right. Oh, I'm screaming. I have a loner on 2 adjacents that is screaming for me to do what? To make a double bond. So let's get rid of that. And let's get rid of that. Let's see if I can get rid of that little line. All right, I now have a molecule with a multiple bond. Are there any loners left? The answer is no, so I'm going to go to my octets. All right, let's start with sulfur. Sulfur, what is your octet? It is 1, It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ah! That's 10 electrons. But remember, I'm the one that unpaired those. If I ever unpair, that's implying that I need to expand. Can sulfur expand? Yes. Because it has N equals 3 or D subshells. All right, so my sulfur is just fine. Let's check the oxygen. Oxygen, what's in your octet? 1, 2, 3, 4, 5, 6, 7, and 8. Is 8 correct for an oxygen? Yes. So it's just fine. Let's check the chlorine. Now if you'll notice, both chlorines are identical. 1, 2, 3, 4, 5, 6, 7, and 8. 1, 2, 3, 4, 5, 6, 7, and 8. Both of the chlorines are absolutely fine. Now remember, they could expand, but they don't have to. They have to have 8 at least. So both of those are fine. So let me get rid of the colors again. All right, I have now checked my octets. I need to check my formal charges. All right, oxygen owns half that, chlorine owns half of that. So sulfur. Sulfur brought 6 to the party, and it owns 1, 2, 3, 4, 5, and 6. So it's overall neutral. All right, oxygen. You brought 6 to the party. How many do you own? 1, 2, 3, 4, 5, and 6. So it's overall neutral. And how about, let's try pink. Chlorine 1 and chlorine 2. So chlorine 1 brought 7 to the party, and it owns 1, 2, 3, 4, 5, 6, 7. And chlorine 2 brought 7 to the party, and it owns 1, 2, 3, 4, 5, 6, and 7. So we have a wonderfully neutral molecule, which we expected because there was no charge on it. So I've checked octets, I've checked formal charges. The next question is, what about resonance structures? What about resonance structures? Go back to black. Let me draw this again. Now notice I changed the angles a little bit, because eventually I'll show you what kind of angles are better than others. But there's the molecule. Did I put a multiple bond in one location when I could have put it in an identical other location? And the answer is no. These two spots, not only did they not want a double bond, but they also are chlorine, not oxygen. So did I put a multiple bond in one location when I could have put it in the others? No. I put a multiple bond, but it didn't have any other choices. So no, there is no resonance structure. All right, chemical common sense. The only thing that was of interest, sulfur. Can it expand? The answer is yes. So this, let me get rid of those. This is the best Lewis structure. That's the best Lewis structure. Now this one is an example of expanding at the beginning. All right, saved one of the best till last. Occasionally, there are some that are a little bit odd that just take a little bit of tweaking right there at the end. And carbon monoxide is one of those. So we're going to put carbon in the center, and it has 1, 2, 3, 4. It has 4 good bonding places. How many things am I trying to put around it? Only 1. So I'm going to put my oxygen on. 1, 2, 3, 4, 5, and 6 valence electrons. Oh, it's screaming. It's screaming. Okay, so I'm gonna double bond that up. Let me get rid of those. Let me get rid of this one. Get rid of that. All right. Do I have any loners left? And the answer is yes. Do I have a lone pair on the central atom that I could unpair? Well, no, because these 2 electrons are on my central atom. So what I need to do now is just pair them up, because electrons do not like to be unpaired. So I'm going to take this one and I'm going to pair it up right there. So I'm going to put it right there, and I'm going to get rid of it from right there. All right, do I have any loners left? The answer is no. Check your octets. 1, 2, 3, 4, 5, and 6. So already I know that something is wrong. I have to have 8 on carbon. So what can I do to get 2 more electrons for carbon? And maybe I can just steal them from the oxygen. So let's just steal those and put them over here. So then I'd have this. Wait a second, are you allowed to just steal? Remember, I'm the one that I'm just visually representing this. The electrons really are always in movement. All right, did that help? 1, 2, 3, 4, 5, 6, 7, and 8. Oh, well, it helped the carbon, but what about the oxygen? Did it help the oxygen? 1, 2, 3, 4, 5, 6. So that was bad, okay? So I shouldn't do that. Well, what if I stole those and put it in? Do you see I'm still not helping the carbon? So the best possibility would be to put in a triple bond. So instead of taking it and giving it to the carbon, I'm going to give it right in there. So let me redraw this. In fact, let's just get rid of this whole thing here. And redraw it. I had this. Right, what I'm going to do is I'm going to take this and I'm going to donate both of them in. Now normally each atom donates one in, but the oxygen is going to donate both of those in, and it's going to make this. Now remember, I donated some from oxygen. It was an unequal sharing, so I'm going to expect some formal charges. All right, let's go back. Are there any loners? No. What about octets? Well, let's check. 1, 2, 3, 4, 5, 6, 7, and 8. So carbon seems perfectly happy. Let's check oxygen. 1, 2, 3, 4, 5, 6, 7, and 8. Oxygen is perfectly happy. So my octets are fine. Let's check our formal charges. Carbon brought 4 to the party, and it is owning 1, 2, 3, 4, and 5. But we expected that because we're the ones that donated it in. So it overall has a -1 charge. And the oxygen is 1, 2, 3, 4, 5. Oh, the oxygen brought 6, and it only owns 5 for an overall +1. So I would put a -1 right there, and I'd put a plus right there. But overall, it's still neutral. So it is not ionic. It is not ionic. It is still neutral, but it does contain formal charges. So let me redraw it. So I have that as my Lewis structure. All right, let's do our last chemical common sense. Octets are fine. Formal charges are a little odd. I don't like formal charges, but was there any way to get around this? Octets had to be complete, so I had to do this unequal sharing. And that leads me to, is the negative on the most electronegative element? Okay, carbon is more positive than oxygen. And yet, look, the positive is on the oxygen and the negative is on the carbon, which seems completely counterintuitive. But the ultimate question is, in order to get the octets full, is that the only thing we could do? And the answer is yes, so we're going to live with it. And yes, this is the correct this is the correct Lewis structure. Now there's something unique about this molecule. It's called carbon monoxide. And you probably recognize that as carbon monoxide as in carbon monoxide poisoning. Yes, the unique thing about this molecule is that this carbon has a partial negative charge or a formal charge, and it does tend to like your hemoglobin or the iron in your blood, so it does tend to try and bond to that instead of diatomic oxygen. All right, that covers one possibility of all the variations. Again, I really highly suggest that you work through all the problems and you go through those mini lectures for each concept, and I will put another lecture of just working through a few Lewis structures. All right, Lewis structures are awesome. Jolley out.